Okay, so this is the review for assignment 2, which is the AST interpreter. Everyone's code seems pretty much great. There were two main gotchas that everyone needs to look out for. So in an interpreter or in any language implementation, the primitive bytecodes are never what you usually get wrong. So what you always get wrong is the correct handling of scopes. So like if statements have their own scope and while statements have their own scope. And this is just really subtle, okay? Because often you don't exercise this code path and it seems to work for many cases. So that's one. And the other part that is always a major source of complexity is the object system. So Feeney has this prototype system where you have to link, go up these parent links. And then when you set a variable, you have to set it at the appropriate stage in the link. So that's also a little bit subtle. So some of you got tripped up by those two things. So those are the main things. As for measurement goes, the main statistic that you guys should have been aware of is this ratio between the time spent looking up an environment versus the total execution time. Okay. So when you looked at the Sudoku benchmark, for example, you would notice that nearly half of the execution time is searching through this environment. The other major statistic is what percentage of method calls is on the integers, right? A normally large amount is just simple integer primitive operations, and yet you're still doing this very expensive general lookup each time. Okay. So mostly that's what we'll be concentrating on for our optimizations. How do you eliminate the time spent looking up environments? And how do you get primitive operations as fast as they should be? Faster. Or at least faster. Okay, so this is just going through, we only had 2 questions this time. So the first one is, how do you extend your AST interpreter to support return? And everyone mentioned one of 2 general ways. So the first way is you take advantage of your language constructs. And in C, that would be long jump and set jump. Okay. So every time you enter a function or you enter a method, you set a jump buffer or jump point. And then when you execute the return, you use long jump to jump out to the nearest jump buffer. Okay. The only tricky part is you have to make sure to handle recursion properly, you have to make sure you save the jump buffer on each new function invocation. And also, just because of the way set jump and long jump is implemented, you need to pass out your return value somewhere. So most people just said, just use a global variable, and that's totally fine. In Java or ML, you do something like throw an exception. In Scheme, you request a continuation. So each language has their own ways of doing this. Okay. So this is method number 1. This is method number 2. So we can augment the return value for eval. So right now eval directly returns the result of the operation. Now we can box it up into this thing. It's either the result, and you wrap up the value in this result struct, or it's a return struct, and you wrap up the value in the return struct. Okay? And then every time you evaluate one of your sub-expressions, you get the thing back and you have to check, is it a result or is it a return? If it's a result, then you proceed as normal. If it's a return, you need to stop evaluating the rest of the sub-expressions and then thread it back up. Okay? So this is probably the cleanest way of doing it, but unfortunately it also takes the most code. So it's probably also the slowest way. Long jump and set jump is extremely fast. Okay. For those Haskell programmers out here, you'll notice this is basically where you might use a monad, but I won't talk about that. So basically, not all languages are created equal. So the implementation with the least code was long jump and set jump. And if your C implementation doesn't have long jump and set jump, then you're forced to do it the other way. Right? So if you're playing around with languages and you're investigating different ways of manipulating control flow, scheme continuations is probably the most powerful construct there is. So I'm just going to throw that out there. Okay. The second big question was on object cloning. Okay. So the first part of it, I asked you to precisely define, give your own definition for what the semantics of cloning are. And basically, I was looking for, are you going to do a shallow clone or are you going to do a deep clone? Okay. And specifically, are you going to do a shallow clone or a deep clone of the parent link? Okay. One or two of you did a semi-shallow, semi-deep clone, and I told you you probably shouldn't define it that way. Okay, so a shallow clone is something where you don't recurse down the clone, you just copy the pointers in your subfields. So if you clone an object and you modify a child object through your reference to that object, then all your clone objects will also see the result. Okay. Is your parent cloned or not cloned? There's good reasons to do either. Various languages in history have done both, so I'm not going to penalize you for that. If you do deep cloning, there's an additional caveat, which is Fini is not a pure language. There's assignment, and because of assignment, you can get these cycles in your object graph. Right? So if you want to do deep cloning, you have to tell me how you're planning on handling these cycles in your object graph. Okay. So semantically, you can define it either way. I think very, very few languages have ever provided a deep clone facility. Not because of any intrinsic difficulty, I think it's just, it's not that useful a lot of the time. Okay, so it cannot be written as a pure Fini function, or if there is, I have no idea how to do it. And to implement it is very easy. You just make a copy, and you copy all the pointers over. Now the next question gives me a chance to monologue for a little bit. So the question is, what are the negative consequences of implementing cloning? Okay. And my sweeping statement about this is that the most powerful language feature is not anything syntactic. It's not like, oh, our language can do it in one line, what he can do in 3 lines, or anything like that. The most powerful language features are the invariance guaranteed by your language. Okay. So, as you'll see, object cloning destroys some invariance. So here's a use case. We want to supply this contract to the programmer, okay? We want to create a function, have a function to create pairs, and it supports getX, getY functions, and setX and setY functions, okay? So really anything that implements this contract should work properly. So let's say you hand this off to a subordinate and he hands you back some code, and this is what he writes. So to track the state of the pair, he allocates an array with 2 elements. Okay, he's going to store x in the first element and 1 in the second element. Sorry, and y in the second element. So getX just returns the first element in A, and getY returns the second element in A. And setX and setY assigned to those slots in the array. Okay? So your subordinate hands you this, and you decide that this is not very good code. Why don't we make it a bit clearer? We only have 2 elements anyway, so let's just declare them like that. Okay. So now you expand the array out into its own individual fields, and then you retrieve from the field and set to the fields directly. Okay. So what's the problem with cloning? Well, for those of you that defined it as shallow cloning, deep cloning doesn't have this problem. But for those of you that define it as shallow cloning, you notice that under a shallow clone, this array is not cloned, right? So this pairs created using the first method, if you clone it, then updates to one pair will affect what the other pair reads. Okay? Whereas in this version, if you clone it, you'll actually get 2 different pairs. Okay. So if you implement shallow cloning, it breaks this invariant. It means that you cannot take that code and transform it to this code and expect it to work in the general case. So the program is not invariant to this transformation under the presence of cloning. Okay. So to me, this is a big no-no. I think this is a really bad property of the language. Okay, so that's a negative consequence. So, like I said, invariants are features. Fini is not a great language, but it's not a horrible one. It has some other invariants as well. So, Fini programs are memory safe. You'll never get a segmentation fault ever, right? So this is something you're used to from GC languages. You cannot write any malicious program in Fini, right? I can take, famous last words. I can take any of your Fini programs, directly run it on my laptop, and assuming I implement the interpreter correctly, there's nothing you can do to my laptop. That is not a challenge. Don't break my laptop.
Would you like to run out of memory?
Okay, and then just one last fun one. So Fini has a while loop, right? So if you write while I is less than 10, then do something. Then outside of the while loop, after the while loop, this is an invariant. You know this is true. I is definitely greater or equal to 10 for this statement. Okay? And this is true in Fini, but it's not true in some other languages. So Dijkstra made a big deal out of this invariant in particular, but I think nowadays we see that it's not such a big deal. Okay, so that's enough for the review.
I have a question.
Oh yeah?
Are there any negative consequences of deep cloning?
Are there negative consequences of deep cloning? I thought long and hard about it. I couldn't really come up with any, actually. Yeah.
Smalltalk has a shallow and deep clone.
So it does have both.
Neither are, well, I think shallow might be implemented as a primitive, but deep is just implemented in Smalltalk using reflection and stuff.
Reflection.
But it actually loops if you have a cycle. It doesn't
It does
know how to deal with cycles. And you find actually, if you start deep copying things, they're often linked to the rest of the system. So bad things happen often. Because it's hard to know when to stop when deep copying. Right? There's usually some programmer intent that knows where the boundary should be, but the system often can't figure it out.
I think that's the primary reason why deep cloning doesn't turn out to be all that useful, because you have this like little pointer link that you forgot to null out or something, and it just ends up making a clone of your entire system.
Can you talk about some of the negative consequences of doing like a half deep clone and half shell, like cloning only the things in your direct parent and then keeping a pointer to the parent?
Oh, okay. So there are some hybrid schemes. Some hybrid schemes I've seen is like for arrays you do a deep clone, but for objects you do a shallow clone and stuff like that. There's the only downside is that you have to explain this to all your users. Yeah. Let's see. How does the power go? Anyways, some language designer made a post that the most awful thing you can do in language design is to design a feature that technically is right but no one gets, because then it's not actually a bug, but you just have to answer everyone's question over and over again. Okay. All right, so the next assignment is to actually write the bytecode compiler yourself. Okay, and then after you do that, then you have like a self-contained Fini system. The compiler is actually not that difficult. It should take you very little time. But I want you to take this time to refactor your bytecode interpreter, because as I said, this is the base that we'll be building everything on top of. So in particular, after the compiler will be garbage collection. And garbage collection can be either difficult or hard depending on how you lay out your values on the heap. So this is a recommendation, a very strong recommendation. When you allocate these values, okay, this is the format I would strongly recommend you to adhere to. Every object has a little word or a cell at the front of the object, specifically at the front of the object. That's some integer that tells you what type of object it is. Okay, so there'll be a special tab for ints, a special tab for nulls, for arrays, and then for classes there will be different tags depending on what class the object is from. Okay. For array, you have a length followed by a variable number of slots. And for objects, you have a parent, and then you have a variable number of slots. That's just for the variable slots. Okay, the method slots don't need to go on here. Okay. And the biggest advantage of this layout is that there are no pointers in this representation.
Sorry. For the class one, don't you want to have a type information as well in some way?
Yeah, okay, so int might be like 0, 1, 2, but then for classes you'll have like 3, 4, 5, 6 for all of them, yeah. Okay, so the biggest advantage of this layout is that you don't need to follow linked lists, okay, and that will make your garbage collection much easier. And also, there's one more.
So something about pointers,
Right.
but I don't think that's true. We still have
Yeah,
pointers.
that's not true. That's not on there. Yeah, so no linked list. Every object is like a flat thing, flat contiguous thing. And also, because all of your tag words are in the front of the object, it makes your heap parsable from one direction, which
Copy that.
Mario said yesterday. Yeah. Okay. So please make this refactoring. Otherwise, your garbage collector will be very difficult to write. And I don't have a slide for it, but I also mentioned in the Piazza post that some of the bytecode operations I consider simple. Simple being defined as it's basically straight line code. It doesn't require any callouts to functions. Okay, so I would recommend doing the cooking phase and making sure as many of your operations are simple as possible. Okay, and the primary reason for this is when you go in and you start generating assembly sequences for your bytecode operations, you don't want to put a function call in there because then you have to deal with calling conventions and all that. Okay. All right, so that's it.
So quick show of hands. Whose bytecode interpreter got faster than their AST interpreter? I assume you took measurements. Yeah. Anyone can get a slower bytecode interpreter? Now, factor 2 or more?
Yeah, 4
Right.
4.
4?
In which
Okay.
direction?
Better or faster. So the idea of the exercises is things are going to get faster and smaller and sort of more efficient and leading up to something that's actually hopefully running quite well. In fact, we were just discussing at the end, I think we're going to have, you can submit your running version, your final version for a sort of a timed competition, and I'll give away a copy of this book. To the fastest one.
Don't do this to me.
Okay, so let's see. Close that. And switch to here. Okay, so I'll wrap up a little bit on some dynamics language techniques, which I think are going to come up in the exercise after the next one. And also we'll summarize a little bit of the stuff that you'll have been exposed to by virtue of reading the Deutsch Schriftmann paper. So hopefully one of the two things maybe will get a little clearer. But then after that, the main purpose of today's session is introduction to memory management. And we'll spend quite a lot of time looking at several different garbage collection techniques. And I'll wake you up when we get to the one that you're going to have to implement. So dynamic languages. I hinted at this last time. The challenges are that you know a lot less in the source. When you see the source of a dynamically typed program, you don't know the types of the things you're operating on, and that sort of cascades into all sorts of other things. So you don't know the types ahead of time. Usually, most dynamic languages allow even programs to create new types at runtime. So it might not even be closed at the beginning of the execution. The types in any particular fragment vary over time. Did you have a question?
Well, can you define dynamic language?
No, not really. Not really. It's one of these things where it's kind of, there's a grey line between the two. But broadly speaking, I would say it's languages where there are no type declarations. If there are type declarations, usually the designer has intended those things to capture some, to basically restrict what's going on at runtime so that you can check ahead of time that those restrictions are met. But that's not universally true. There are type systems that don't satisfy that or that provide other guarantees. But broadly speaking, you don't know what's happening until you actually get to run the particular fragment of code. So let's look at some examples. So if I write f(x, y) and there are no type declarations, who knows? You know, what's x, what's y? They could be of any kind of value. And here's a typical example familiar from anyone who's used the dynamic language. You can, call the same function with ints and floats, and the program has to figure it out at runtime. You might even be able to call intermingle structured and unstructured things. So if f in JavaScript was the plus operator, both of those would be legal, right? Because plus is addition and string concatenation. And then you could do reflective stuff. You can have strings passed in. This could be a string typed in by the user, which you're going to eval. Is going to cause a piece of program to run, and you can't, in principle, know what that's going to do ahead of time because you can't read the user's mind. And you could even maybe be able to redefine chunks of the program through reflection. I'm not saying that that's a good idea, but implementations have to deal with it.
There are type systems that allow you to do this and still have the same amount of safety as if you had each one individually.
Yeah, but no one understands them. to a first approximation.
Really? Okay.
to a first approximation. Okay. So let's look at a little bit in more detail about what the consequences are, in particular what the implementation tricks are to optimize these things at runtime. So we don't have any type information on the variables, but that doesn't mean that the values don't carry their own type information, right? It's not like C, where C just operates on strings of bits in memory, and you can kind of operate on anything, right? You can write a union which has an int and a float and a string pointer and anything, and you just choose which flavor of the union you want to operate on, and it looks at the bits and treats them like that. Now, I should point out, even C says that behavior is undefined, right? What happens in that case is not defined by the C language, but there are conventions that all the implementations follow, and people depend on that stuff. But you can basically subvert the type system, and you're sort of encouraged to subvert the type system in the name of system programming. In dynamic languages, you can't subvert the type system. It's just that there aren't any types declared on the variables. The types are sort of associated with the values. So the idea is if you have an object and you try and do some operation on that object which isn't defined by that object, then you should get a runtime error. And so we have to be able to both figure out what we're supposed to be doing and also whether that's allowed by the language at runtime. Obviously values vary in their space requirements, and so when we allocate space for a variable, you've got two choices. You either make it as big as it's ever going to have to be to accommodate all the choices that might be there, or you more typically use an indirection. So the variable, basically what happens in most of these languages, all variables become pointers to something, to a value. You can, in some languages, get away with the former. I think I have, I'll look ahead and see whether there's an example of that. I don't seem to have an example, but for example, in BASIC, right, you write a string, it has a $sign after it. The other variables don't have the $signs, or they don't have array brackets, and those are all scalar variables, at least the early versions of BASIC. So you could tell just by looking at the lexical structure of the variable name whether it was a scalar or whether it was going to be a structured thing. And if it was a structured thing, you'd need a pointer, and if it was a scalar, you could just hold a value, reserve a space big enough for a number, and you'd get away with it. Okay, so let's have a look at an example of this. And what I'm going to do is take that little expression bytecode interpreter. I'm going to change the assumption, change it so that any variable can hold an int or a float at any time. So now it's not a typed system, and now the bytecodes are untyped in that the bytecodes just tell you what operation you're supposed to perform, and the underlying representation has to figure out what's going on. So if, and the rule I'm putting in place here is if you write an expression using floats, then you sort of widen to floats wherever necessary. So in this particular case, because I'm not having any structured variables, I can allocate for the biggest case. I don't need to do an indirection. I can use a C union to have a space that's big enough for an int or a float, whichever of those is bigger, and use that as my value type. And then all of the elements in the interpreter are just made of that value type. So the stack and the variables just contain those unions with a tag to tell me which particular one is in use at any particular time. So now we've gone from a simple scalar in the implementation to a slightly more complicated structure, but not very complicated. And what does the interpreter look like? It's a little bit more tricky, but not bad. Again, I've kind of unfolded everything here, so you see through to the bottom. Typically this will be more wrapped in macros to make it a little bit more abstract, but if you read through this, you can see exactly what's going on. So in this case, I have a literal which pushes an int onto the stack. I'm going to increment the stack pointer. In this case, I'm doing checks on max depth of the stack for checking whether an error occurs if I overflow the stack. Otherwise, I push a value onto the top of the stack, which is tagged as an int and then has the integer extracted from the 4 bytes that follow the bytecode for the literal int. And then for add, now I have a little bit more complexity because I have to figure out exactly what I'm adding. And what I'm adding is determined by the types of the 2 things on the top of the stack. So if the 2 things on the top of the stack are integers, I'm going to do an int add. Now C makes this less obvious than it might be by the fact that C does automatic conversions when you mix ints and floats. So for a little bit more clarity here, I've put explicit casts in where I'm actually going from integers to floats. So in the case where we've got 2 ints, I just do an int add. If I've got a float and an int, then I have to cast the int to a float and then add that to the float. When they're both floats, I'm doing the float add, and when I'm doing the other direction around, I'm doing another cast. But it's all fairly straightforward, nothing too tricky there. And then for the get operation, which is just reading a variable, then we can use the C structure copy to copy both the tag and the value at the same time. Hopefully that's pretty straightforward and clear. Any questions? Okay. If we were going to do the abstract interpretation of this bytecode, we could do that in this particular case by modeling a stack with types only. We don't need the values now. So this might be something you would do if you were going to do a pre-pass over the bytecodes to figure out the type of an expression or to figure out in advance whether a particular operator was going to do an integer or a floating point add. And so this is the replacement for the earlier abstract interpreter you saw. So here we're just pushing tags onto the stack which represent the type of the thing that we're computing with. Now, suppose I had division here, and suppose I changed it so that the division operator, if the 2 things were if it was equally divisible, it put an int on the stack, and if it was a fraction, it put a float on the stack. How would that affect what was going on? Could I do that in this scheme?
You wouldn't be able to do abstract interpretation.
Exactly. Exactly. Because now the specific values at runtime define the types on the stack. They're not uniform overall input values, and so you can't model abstractly what's going on and get an answer. You'd have to extend the type system to carry that uncertainty along with it. And you might end up with something that was so conservative that it was useless because it would sort of always just degenerate a flow. But in the case where you didn't have a division, it would still be fine. The other thing you can do with an interpretation like this is just use it to model a stack depth. And so if you, even in the case where you're doing the conversion trick, if you can model the stack depth accurately, that gives you the chance of removing these stack tests. If you know it's not going to overflow, if you can always allocate enough stack for the worst case, then you can remove the stack checks even if you don't know the type information. In the JVM, as you've seen, this is basically done twice. Once by Java-C, when it generates the type information that it's putting out, it has to compute this model so that it can know that it's generating the right bytecodes. And then again at verification time when the bytecodes are run. Okay, so that trick works fine on small data where you can allocate for the worst case, but it doesn't work for large data. So if you imagine a language in which a variable can reference a Boolean or a million element array, we clearly can't allocate for the worst case there. Even if we wanted to allocate for the million elements, right, it might be a billion or a trillion or some other number. So in that case, we need to use an indirection to reference the value, and at the end of the indirection, we allocate a cell that's big enough to hold the data that we're executing, in effect, in the heap. And of course, the other thing that gives us is sharing, because now we can pass pointers to things around instead of passing the values. So that might be important in the language semantics too. So in effect, every variable now contains an address, or equivalently, an index into some kind of table which contains an address. And we'll look at that. As I said, BASIC only needs the indirections on arrays and strings. I think there are other languages that have that sort of syntactic flavor on some of the variable types.
The older papers often talk about using an object table. What is the main difference between that?
We'll get to that. Okay. So imagine we have now a language in which we can have simple types and some structured types. So in this case, I have an integer, a floating point number, and an object containing an integer and a floating point number. How would that look in the heap? Well, if we had a direct heap organization, each of the variables would contain the address of a cell which contains the value that we're interested in, but it has to also carry the type information around with it so that we can tell dynamically what the associated value is. So typically when you allocate these contiguous objects that Patrick was mentioning. You put some stuff in a header, there's usually some amount of bookkeeping information that goes in there. We'll see some of the information that might be required for a garbage collector later on today. If the language was class-based, you'd probably have a reference to the class or some other type information in a known location here. So the point here is that the first two words in these cells always looks the same. It's always the header followed by the class, so that whenever you get a pointer to something, you can figure out what the class is without knowing the class. Otherwise you end up with this horrible circular thing that you have to find the type of something, and to do that you have to know its type. So you have to have something nailed down in a fixed location, and then after that you can have variable amounts of information. And in this case I have an extra cell for integers which contains the integer value, one for floats which contains the floating point value, and for the points, I store the x and y in order. And then off to the side you'll have your metadata that describes what's going on in each of these cells. So these, I've drawn this as three separate columns, and they could indeed be three separate areas in your implementation. For example, the named variables could all be on the stack, this could all be on the heap, and this could all be metadata. For example, if you're compiling a language that has all of the classes embedded in the source, you could generate all of this at compile time, and it like the constant pool, right? It's metadata, it's off to the side. But it need not be like that. It can be two different areas. For example, these things might be runtime objects as well. For example, if you get to load stuff dynamically, this all might be the heap. And if you go as far as something like Smalltalk, where stack frames are objects, then these are also in the heap. So it all depends on your semantics and what you're trying to model as to how you partition things. You actually find that making it uniform and using a single thing for everything is simpler, because you end up by writing only one allocator, one garbage collector. You don't have to do separate management. But the characteristics of these things tend to have sort of very different longevities, right? These things tend to last for most of the life of the program, whereas these things come and go fairly frequently, and stack frames come and go really frequently. So putting them all in the same structure will be easier, but probably slower in the long term. And so as you look at more tuned implementations, they tend to try and separate these things out and deal with them using special purpose techniques tuned to the individual behaviors. Now, if you're going to do this with an object table, what you do is you'd add somewhere in here a table which basically contains a pointer to every object in the system. And instead of the picture that you see there, we'd now substitute each pointer with a pointer into the table, and then the table pointing to the actual object. So we're adding an extra level of indirection here. Every pointer goes through the table to its ultimate destination. And if your classes are also objects, then those would also go through the same table. What that gives us is now every allocated cell is only pointed to from one place in this object table. So if we want to change this, we want to move it somewhere else, or we want to resize it, which often means moving it somewhere else, then we only have to find the place that it's pointed to from this table to do that, instead of finding all the pointers to it, as we would have had to do before. These things need not be actual pointers. They can be indices, right? Because this is probably a contiguous table allocated as an array, elements 0 to whatever. And so these can just be indices into the table. And the other benefit of doing that is, if the table is a lot smaller than the address space, then the width of the indices can be a lot smaller than a full pointer. So if you want a nice compact implementation with restricted numbers of objects, you can make this table 16 bits or 32 bits or whatever, and define the pointers, the indices, as much narrower because of that, which makes a much better use of the space.
Is this commonly done in high performance?
We'll get to that. Not anymore usually.
Because it seems really.
Yeah. So there are a couple of penalties for doing this. One is it's slow, right? Now, when this stuff was common in the 60s and the 70s, it wasn't slow, because the cycle time of the machine was usually the same as the cycle time of the memory, or very close to it. And so going the extra indirection was like one extra cycle or two. It wasn't a big deal. Now, of course, that's not true anymore. So there's a big performance penalty of putting that table in memory. It also costs you some extra memory, right? Because we've got an extra slot now off to the side for every object. Anybody give an idea for how much? What's your guess for how much extra an object table costs in memory footprint? Okay, hands for those who think it's 2x. 1.5, 1.3, 1.1, 1.01. Okay. So a good rule of thumb here, one of the things I've observed in looking at a lot of different object systems over time is that when the object size is defined, when objects are defined by programmers cognitively can't think of more than a certain number of objects, fields in an object, before they say, oh, it's too big now, and they split it into a smaller thing. And so you tend to get the average object size somewhere around 7 to 10 fields. Very common, very common. And with this very bimodal distribution of arrays are way off to the side. Arrays tend to be big, but named things tend to be small. And so with a 10-field system, if the average is 10, then it's an extra 10%, typically, in your space footprint by having that level of interaction. It's not a massive cost. The cost is really more the time cost. of doing the indirection afterwards, the animation.
Is that slow?
There's got to be a shortcut that bypasses this. Okay, but it does also allow, as I mentioned, incremental relocation of objects, because now you can move one and you only have to change its address in one place, which, as you will see, can make for a much easier life in some cases. Now, this was the sort of the way most things were done through to around the mid-80s. And then Dave Unger's PhD thesis here in 1986 kind of established that not really such a good idea anymore. You know, he did a lot of measurement and analysis and came up with an alternate GC system which did compaction and garbage collection without needing the extra indirections and stuff. And sort of it's been pretty much abandoned since then as a high performance way to go. It's still used a lot in systems in which footprint, you know, if you can compress the pointers down, you can get your 10% back easily if you can make every 64-bit pointer into a 24-bit pointer, because there are a lot more pointers on the right than there are slots on the left. So in small systems, sometimes it's used as a trick just for encoding addresses into a compact space. But it's not very common these days.
Maybe in the embedded space.
Yeah. It enables these other operations to be done in constant time. So in places where you need constant time guarantees on some of the other memory management operations, it's also a benefit. You'll see as we go along that all of these decisions sort of tie together in holistic ways. And so you can't just sort of pick the best in class of any individual technique, put them all together and end up with what you want. Usually you end up with a particular desired direction in terms of what your footprint wants to be or pause times that you want to admit, and that then guides you to other choices which are interrelated. It's hard to put that on a slide, interrelations.
Couldn't you cache the translation?
I'm sorry?
Couldn't you cache the translation?
Still be stuff.
You could, but we're going to watch it again. But there are a lot of these, and they're changing a lot. And so the hit rate on a translation here is probably not going to be that high. I mean, or rather, the miss rate is going to be high enough that it's going to be hard to amortize. So if there were hardware support for this, sure, you could do that effectively. But in software, what would you be doing? You'd be having some kind of table off to the side indexed by this that would give you, you know, that would save you a load, right? I mean, how do you do that without having a load in the table?
Translation look-aside buffer.
Yeah, so the obvious way is to make this look like a TLB, but the problem there is that for any reasonable system, there's going to be tens or hundreds of thousands of these things, or maybe millions. No one's going to go build you an MMU that big. You know, that's a big piece of associative memory, right? Associative memory is sort of practical in numbers of up to 1,000, but not hundreds of thousands.
I don't think it's a good idea, but a TLB lives and dies on the idea that not much is actually used.
Yeah, well, so the problem is, and I can speak to this with some authority because I've done some measurements in written papers in this area, is that the usage of this is much bigger than the usage of a TLB, and there's a simple reason for this, right? Each one of these is associated with 10 words on average, whereas each entry in a page table is associated with 10 kilobytes. And so there's a factor of 100 or more in terms of the coverage of memory from each one of those entries. And so for the same working set, you're going to need 10 to 100 more of them.
So for the object table, every time you create a new object, you also need to create a new ID for the object, the object table. So when you run garbage collection, you also need to garbage collect the object table. Is that right?
Well, what happens is that the unused entries here are threaded using a linked list. So you have a free list going through there, which is easy because they're all the same size.
Okay.
When you want to allocate one, you pull one off the free list and use the next one. when you reclaim an object, you have to put the associated ID back on the free list.
I see.
What tends to happen is that the order of things in here gets all jumbled up, and so the locality in the actual object table itself sort of goes to hell over time.
And this is all for reference counter systems, I assume.
No, both ways. Both ways. So the Deutsch Schiffman system used an object table. That Smalltalk system used an object table, and I think still does. I couldn't find, certainly Peter didn't know of any rewrite that had been done that removed the object table. I'd have to talk to one of the more modern maintainers to see whether they've changed it since, but throughout its life it was an object table based implementation. There's got to be a way of doing this.
Should you on timer or something?
Option right. Apple right. Control right. Okay. Either way, whether it's with an object table or not, basic arithmetic operations in this arrangement are painful, because imagine what we're going to do now if we're going to do a simple addition and an assignment, right? So now, instead of I containing a number, it contains a pointer to a cell that contains a number, and our 123 is presumably off somewhere also in a cell. So assume that this is, is really I plus j rather than I plus a constant. How do we implement this? Okay, so we firstly have to extract the values out of the cells, then do the arithmetic. Then we have to make a new cell, because we can't reuse the old one. Right? We can't store the 126 in here, because now everybody who shares this value, right, because when we pass parameters, we pass pointers, we don't make copies. Everybody who shares this would see the value 123 become the value 3 become 126, which is generally speaking not considered good language semantics. So we have to make a new cell and store the new value in that, and that's the expense here, right? Now we're generating these cells like they were going out of fashion. The other thing is, of course, this is now going to put a huge load on the garbage collector. So, give me a guess as to how much slower your language goes if you make this transition from primitive numbers with primitive operations to boxed numbers. Anyone got a sense for, take any sort of normal program and do that rewrite, and how much slower do you think it will go? Like factor 2?
3 to 4x.
More like 5 to 10. It's a pretty big hit. It's a pretty big hit because arithmetic is really common, and now you're just doing a ton of work for every arithmetic operation. Okay, so there's the result. Now we store a pointer, and we have to garbage collect if those things are not referenced anymore. So there's a
The instruction set really needs tagged arithmetic.
yeah, that's what we're. So we've got these primitives in the heap, and they're costly. They have all this high allocation and deallocation cost, and the memory overheads, and the load and store penalty of every indirection that we have to do. So the one alternative allowed anyway, is to restrict the value range of our primitives and squish them into a slightly smaller space, and use the freed up bit or bits to represent the tag information. So here's an example. Typically on a word-aligned machine, for example, a 32-bit machine, objects will start on 4-byte boundaries, which means every address has 2 zeros at the bottom. If we put type information into the 2 low-order bits, for example, we use 2 zeros for addresses and a different combination for some other thing, then we can use the remaining 30 bits to contain primitive data. So in a 32-bit word, the 2 low-order bits would tell us what the other 30 bits mean. If the 2 low-order bits are 0, then the rest of it is an address and a pointer to an object in the heap. the two low order bits are 0, 1, we have a character. If the two low order bits are 1, 0, I mean, you can make these choices arbitrarily, right? This is just one example. But the two that you always want are address and integer. Those are by far the most common two. So sometimes people use only one bit. But for 32-bit machines, which are very widespread, that 2-bit advantage is often pressed into service.
Sorry, I think I should just mention now. For your assignment, I'm going to stress that your integers be tagged 0, 0. For reasons you'll see.
Okay. I'll show a couple of alternatives, because there are pros and cons to different tagging schemes. So in this scheme now, we have to do the tag test before we do anything else. You have to look at those two low order bits. If the tags are 0, we can do an object access. If the tags are non-zero for ints, then we have to strip them before we do integer arithmetic. Now for floats, what do we do with floats? I mean, you've got a sign, a mantissa, and exponent. Which part are you going to squeeze out? Who thinks we lose the sign bit? The mantissa?
Yeah.
Exponent. Bad idea to shrink the mantissa. Bad idea. Decrease the range. Don't decrease the precision. There's already not enough precision anyway in a 32-bit and 32-bit float. So you really probably want to chop out a couple of bits of mantissa, and you just end up having a smaller range of floating points.
So you're trying to chop off the exponent?
I'm sorry?
What do you mean chop
Sorry,
off?
the exponent, yes.
I can't remember which one.
Of course, now imagine what you have to do to do a floating point add, right? Because now the floating point adds are not in the hardware format. So there's some bit twiddling to be done on every datum before you present it to a floating point instruction, which is much more expensive probably than the floating point instruction is itself these days. This again was a great idea in the days when all floating point was done in software. So there's some alternatives which sort of shuffle the pain around into different places. One alternative is to use 0, 0 for integers and 1, 1 for addresses. And that means that integer arithmetic doesn't need to strip or replace tags. You can just do the addition in effect on multiples of 4. And most things are pretty cheap. You still have to do the test, of course. And removing the tag before the load and the store is, small compared to the cost of the load of the store. At least that's the reasoning. And it might even not be necessary if you're using index loads to do field accesses. So when we get to compiling, the way you compile field loads is a load with an offset, and now all you're doing is subtracting 3 from the offset, in effect, adding 3. The other nice thing this gets you is if the addresses are unaligned and you forget to do this in your implementation, you'll get an unaligned hardware exception almost certainly in most systems that say, you tried to load a word from this address that's not word aligned. So that's an alternative. I have some example code of the expression evaluator, and you'll be doing something like this in a future exercise to your Feeney implementation. So you start off by type defing some flavor of int that's big enough, because C doesn't tell you what the size of ints are, so you have to figure out for your implementation what size is the right size and type def that to be a word. And then in this case I've encoded the tags so that 0 is an int, 1 is a float, and 1, 1 is an object, and I have a bunch of macros now to do manipulation of the associated words, because you don't want function calls on all of this stuff. That will kill your performance too, because you're doing a lot of tag arithmetic now. So I have a way of stripping the tag off. I have a simple way of testing whether the tag is an int or a float or an object, and pulling out the underlying value. The float ones I kind of just elided on the horrible bit twiddling. That would be functions off to the side that you'd have to do stuff with unions and bit fields and look in the IEEE manual and stuff like that to figure out exactly where the bits are, which I couldn't be bothered doing that. And then for objects, we have a way of stripping off the tag and a way of basically converting an int to an object to its underlying address. And then our stacks variables are just these tagged words. What does it look like in the interpreter?
I think there was a typo in there. You have use tag of, and then above there you have tag.
Oh, on the next.
No, right here. So you have
Yeah,
tag
you're
there,
right.
but you-
You're right. Yeah. Okay. I've just illustrated add here. So in this case, I'm using the macros to make them a little bit more readable. So isInt is the thing that tests for an int tag. If the two things are int tags, then we have to pull out the int values and then do the conversion and then put them back again. And the macros here just kind of hide the fact that in this particular case, I think we don't do anything. And then similar things for the flow. And again, by macroizing things, you can make this code fairly readable. I don't think there's anything particularly unusual or noteworthy here. No, you just got to get all the cases right. Fairly straightforward. This was a common technique in language implementation, used a lot in Lisp systems and Smalltalk and others. And in the 70s and the 80s, special purpose Lisp machines were quite popular. There were quite a few companies building them. And quite a few systems used hardware support for tagging. So this format, the representation of some number of bits in a word, was actually understood by some of the instructions in the machine. And you could leverage that to give you higher performance. So for example, if you did a tagged add, the tagged add operation could strip the tags and check them in parallel with doing the arithmetic. So that the actual cycle time of the add was no worse, and if the tags were incompatible, well, they gave you some combination that the instruction couldn't handle, it would either set a flag or raise an exception. So that was fairly common, and in fact, Spark, when it got introduced, was right around the time where this was still fairly widely used, and it has support for some instructions that do this. So there's the tagged add and subtract, two flavors of each. One that just sets and modifies the integer condition codes, and the other one does a trap when there's a combination error, basically, between the tags. There's a trap on overflow, which is kind of confusing because it's not an overflow, it's a tag error. There's no separate trap for tag errors. So the overflow handler has to figure out exactly what's going on. So these were put in Spark. Unfortunately, the trap overhead is so high that I don't think these ever really got used because it turns out it's just cheaper. In Smalltalk, for example, the frequency of a plus operation being something other than ints, like floats, is common enough that it's just cheaper to check before you do this instruction than pay the price of the trap on the 1 in 100 that actually invokes the trap. So the trapped ones were sort of a disaster. And these ones got used a little bit. But as Peter mentioned last week, there are compiler techniques that we'll get to that can lessen the impact of the tagging. The good thing about tagging is that there's no memory operations involved. It's just sort of register to register stuff. You're just fiddling around with the bits, and that's still cheap. Right? The memory, the loads and the stores have got worse and worse over time, but the bit twiddling in registers is still cheap. So tag manipulation is not too bad.
Is it, since it's baked into the hardware, does it mandate a specific tagging scheme?
Yes.
Oh, okay.
Yes.
So does this mean that the decision whether or not to use tagged arithmetic is on the language and not on the implementation? Because the use of tagged arithmetic will necessarily change the range of, for example, the
Yeah. So it depends on what your language is willing to admit. Whether it says, if it says, integers are some size that is implementation defined, of course, you just say, okay, now they're 30 bits, and too bad. But in things like Smalltalk, integers don't overflow. When you add two numbers together and they don't fit in 30 bits, then it goes to a heap cell representation. So from that point of view, there's a discontinuity in performance, but not in behavior. Other languages have different decisions on this. JavaScript tends to do tagging for all its variables. I don't know how it does that, whether it restricts floating point ranges to some smaller value, because in general, sort of the default value in.
62 bits.
So you get 62 bits of. But does it reduce the mantissa?
I don't know this.
Okay, probably maybe on the 64-bit number, maybe you can reduce the mantissa rather than the exponent because you don't care on a double. But yeah, there's that's definitely a price you pay. Okay, so at some point you'll be doing this, adding tagged arithmetic to your Feeney interpreter, and measuring what difference it makes on your performance. Okay, so other thing I want to talk about is the absence of static type information on code. So we talked about data. Yeah, sorry.
Tag. When you say tag arithmetic in Feeney, like there's no add instruction. It's all like function calls, right? So
Method calls.
or method calls.
Yes, but that you can still in the method you can do the right thing. It's a representational change, and what it should give you is the ability to do arithmetic without having to allocate for the cells for the values.
Okay.
Does that make sense?
I'll think about it.
Okay, well, we can talk at the break if you have other questions. Okay. So for code, the biggest downside of this is now you see an invocation and you don't know what you're invoking statically because you don't know what X is. There's no type system giving you that. So it could be invoking the F method in any class that defines it, or it could be trying to invoke it in a class that doesn't define it, which is an error. You have this new class of error now, which is, I'm calling something which isn't there in the particular object I'm calling it on. So the implementation has to deal with that. And in the worst case, you're doing, a full lookup and dispatch for every invocation, which is really painful. Now, many of the dynamic languages, to give you sort of a more powerful abstraction, they tend to put all of the primitive operations under sort of a method lookup semantics. So pluses and minuses and sometimes control structures, they're all in theory done through the same invocation mechanism. And so if you had a full lookup and dispatch for every single one of these, the performance would be truly awful. And so making these things go at least a little bit faster is really critical for performance in most dynamic languages. So you want things like addition and subtraction and variable assignment and if tests and stuff like that to have some reasonable performance, not a full lookup on every operation. So some examples in JavaScript, right? A plus B, it could be a flow add. Most implementations optimize the case where the parameters are integers and have a separate tagged representation of integers and would do an int as an operation. It could also be string concatenation. If I write A plus B in Smalltalk, it means send plus to A with B as an argument. And any class can define plus to do anything it likes. But in Self, it goes even one further in that the control structures are dispatches. So the way to read this is we do a test A less than B. That's a send of less to A with B as a parameter. And that gives us one of two objects back, the true object or the false object. And we send to that a closure, a pair of closures, one for the true case and one with the false case. And the true object evaluates that by evaluating the true closure, and the false one evaluates the false closure. So even in this case, control is a full dispatch and a closure evaluation implemented naively, which is really, really painful. And then when we're finally done, this assignment is also, all assignments in Self are also fully looked up dispatches in theory. And then in R, the square brackets are methods, and you can redefine what those do. So you can't even look up an element of an array without invoking a method. So you've got to deal with eliminating this lookup cost as much as you can to get something that's even half reasonable performance. In most of these languages, so firstly the lookup is very language specific. The semantics of what it means and how it operates is language specific. So you have to look at what a specific language mandates. But in general, In most cases, the target method is determined by two or a small number of things in the call. Typically, the class or the type of the receiver, the thing on the left usually, and the name of the method. It's usually that combination determines the lookup. And for that, if that's the case, we can use a simple global method lookup cache to try and speed things up. And this is like the simplest speed up technique. What we're going to do here, I have a cartoon here that we're invoking x.f. X refers to one of these objects. In this case, it's an int containing the value 3. The object refers to its class, which contains a bunch of methods. And the method name points to the code of the method, which has the bytecodes in. And normally what you'd do is you'd follow the pointer from the variable to the object, you get a value, okay, it's 3, follow that from the class to the method, you look down this list, trying to find a match of the names and invoke the code. And if this was if you had inheritance, this would have a pointer to a superclass, and you'd follow the pointer to the superclass, etc., etc. What we can do instead is do a simple hash. And in this case, what we're doing is we're hashing the class with the name of the method. We're computing some bit string that's derived from those two. And off to the side, we have a table that's probed by this bit string that contains, the true values, in this case, int and f. And a hit would be a pointer directly to the bytecodes. And so, in this case, when we're doing the hash lookup, we're just going to find the class, we're going to get the name, which is usually there as a literal in the bytecode, do a simple arithmetic thing, usually some XORs and bit strings, probe this guy. If these two match those two, then we're off to the races, we have our bytecodes, and we can start executing without having to go through all the intermediate stuff. And this is pretty effective at making stuff faster. How's this modified by tagging? Suppose X is tagged. What else do I have to do?
Show the tag bits first?
Yeah, so I have to look at the tag bits and figure out whether it is indeed a pointer to an object or whether it's a primitive type. And if it's a primitive type, then I'll probably have a direct pointer to the classes of those things in my hand. I'll just keep those around as constants, so I can basically do that translation from variable to class as a constant time lookup. And then I hash based on that class and the name, and we can go do the same thing. So it just saves, it adds an extra test at the beginning, that's all. Stripping of the tag bits. So I'm not going to walk you through all the code for this, but I'll give you a flavor of how it works. This is lifted directly out of that Smalltalk interpreter that I ran last week on the screen, which was my master's thesis interpreter. And that's basically a C clone of the Smalltalk book. And in that, there's a cache which has 4 entries in every entry, 4 fields in every entry. The selector, which is a reference to the name of the method, is basically a symbol. The class, a pointer to the thing we're going to call, the method itself. And in Smalltalk, the way you invoke primitives is that in place of a method body, you can have a number, which is basically a vector into a primitive table off to the side. So if it has a primitive index that's non-zero, then we're calling one of those primitives instead of executing bytecodes. So with that structure then, the method lookup routine looks something like this. So in this case, we're sending a selector to a class. Because it's a bytecode interpreter, a lot of the state is kept as global variables. In this case, the message selector was pulled out from the bytecode and is often a global variable, but the class is passed in as a parameter. In this case, we do an XOR between those 2 bit strings, modulo the cache size, which has to be a power of 2. And then we look up an entry in the cache, check whether we've got the match, the selector and class fields hit. If so, we set the global variables that are the place we're going to go to next when we're executing. Otherwise, in this particular case, this cache doesn't do any reprobes. It just goes up to the full lookup if it misses the first time. There's many papers have been written about alternate schemes for dealing with these caches and reprobing and all of that stuff. But this is such a simple technique that it's not worth optimizing. You want to put in better techniques rather than working on speeding this up. So this does a full lookup otherwise, which sets the same variables, and then populates the cache with what it looked up, and then off we go, executing the next method.
One question.
Yeah.
So you're saying like you might not always update the cache on a miss. And that
No, in this case, it always updates the cache.
Right, but you could have another schema which didn't update the cache.
Well, no, what you end up with is different caching structures like the inline caches, which are not, this is a global cache, this is one for everything, and it's just hard to make the hit rate on this really, really good or the reprobes really effective. It's sort of okay for a low-level, simple implementation without high performance, but rather than spend a lot of time tuning this, it's better just to put in a better technique.
How big is the cache?
Usually order about 1,000 entries. Sort of, you know, more 3 digits or more, but not more than 4 digits. It rarely any point in having it bigger than that. So the alternate scheme, which we'll look at in some more detail, the better scheme is to use a call side cache. So instead of caching globally and doing the cross product of the pairs into a single global cache, is to have a call side cache, which was introduced in the paper last week, which is and then you do the other tricks with compilation to put the branching in speculatively. But we'll look at sort of how to implement this when we look at compiling in a bit more detail. So another thing probably coming up is adding a method lookup cache into your interpreter and seeing how it speeds up. Just a simple one of these should make some difference. Okay, so that ends the section. We'll take a break and then we'll come back to memory management after the break. Are there any closing questions on that material? Okay. Oh, actually, what we'll do is after the break, we'll have a couple of presentations from the submitted set. So let me look up the names.
Tonight, right?
By today.
Right, by today, so tonight.
Yeah,
Sure. I've already done that in some of the slides.
Okay, and I think up and down arrow will get you where you want to be.
Okay, and yeah, Jack isn't here today, so I'm just gonna be alone on this, I guess. All right. So is this in presentation mode?
It's just a web page. It's
Okay.
just the
So
web
I guess I'll
page.
just go to the next one.
Yeah.
All right.
Down
So-
arrow will do the right thing.
So we made some new assumptions to try to simplify the bytecode. Is conceptually there's no, or first of all, like we talked about like Java having annotations like 2 weeks ago in the class file, which is basically what's used to do type checking among other things now. So figure why not just make use of those annotations? Why do we need type-based bytecodes, which is I think kind of the common idea most people follow. And you can also use the same thing to probably ensure data hiding. So you can like kind of do an abstract interpretation like, okay, are we trying to access a field or a method that's private or protected in an invalid context? And the other thing is forget in the bytecode spec, completely forget about having different integer and float sizes. Everything is 8 bytes. This makes everything so much simpler conceptually. But the implementation can handle it however it wants, because that's obviously wasteful and inefficient. Finally, we just try to retain a lot of the Java specs, so we don't want to modify a lot of the structures in the constant pool. Just want to keep that, change the bytecode set without changing too much of the way the data structures are implemented and added and stuff like that. So this is a bytecode set. It's cut down to 48 bytecode instructions from what I counted was about like 160, 170 in the original spec. It's like not bad. Could have done better, I guess. Probably notice some things. There's a lot of things that stay from Java, but some things definitely like all the type-based stuff is all gone. And I'll walk through like each of these sections. The only section I think I don't walk through is synchronization, because that's exactly
like the Java bytecode spec. Like we make no changes to that. So without further ado, constants. So we put a null constant on the stack. So that I think there is something in the Java bytecode for that. So or like a null object. You can put a constant on the stack. So it's an opcode plus the 8-byte constant. Just very simple, just a literal. Wasteful for smaller types, but it simplifies the bytecode if the implementation wants to do something smarter, go ahead. But I mean, bytecode size isn't really that much of a worry from my understanding, but someone could probably correct me on that. And then we introduced a new type that's void, and it's invalid to do anything with void except just removing it from the stack. And the reason it's there is just so that return, you'll see later that it just makes return like kind of uniform. Like you can do one return for whatever type. You don't need a separate return for void. And so in control flow, we kind of took the idea from the Java bytecode instruction compare, which just gives either a -1, a 0, or a 1 onto the stack. It's used to compare addresses and integers, and we needed a separate floating point one because you can't just do a naive greater than or less than on an integer type and expect to get the right answer for floats. So that's kind of like the one downside. We figured that because of the complications of floating point types, we kind of just ended up having to do this. But compare eliminates a lot of the other things, so we don't need a greater than, greater equal, less than equal, because we can just use this one and plus arithmetic for everything. So we have an if as well, which is just a branch. It's 2 branch offset bytes instead of 1. So basically, I think there was multiple different ifs in the Java bytecode to handle like a 1 byte offset and a 2 byte offset. Just went for the higher one. Like you don't need one or the other. At least I don't think so. So it just pops one value off the upper end stack, compares it to 0, branches of true. Goto is the same as Java Goto, except branch offset is 4 bytes by default, so you don't have a Goto_W that has 4 byte offset, right? You just have one Goto. Instance of is the same as Java instance of, and return is exactly the same as the Java bytecode. So you pop the top thing off the upper end stack, go back to the previous frame and put it on, except you don't care about what the type is because everything is fixed with. And if you can put a void on the stack in the void case. So stack manipulation. Just pop is the same. It pops one value. Dupe, same thing. Pop duplicates the top value. Swap. So we eliminated a lot of the stack manipulation instructions by simply having one swap that has 2 unsigned byte offsets, which basically tells you what 2 positions on the stack do you want to swap. So this way, all of these dupe 2, dupe x1, dupe x2, dupe 2 x1, you don't need them anymore because you can just use any number of swaps and dupes to do it. Like it's slower, but the bytecode set is much, much simpler. Next is bit manipulation, also fairly straightforward. Bit manipulation is only defined for unsigned integer types, but again, the type checker can, or the verifier can make sure that you never run any of these bytecode instructions on something that's like a float type or like an address or something like that. Next we have arithmetic operators. Again, we couldn't really get past having float because we do need to handle float types separately. They are fundamentally different. We also need instructions to make the explicit cast to, one, help the verifier, and also, when we're actually when the code is actually running, you know, like kind of what type, that the instruction is right. So next, variable manipulation, load and store. Get rid of all typed load and stores. Just every byte offset is it's a byte offset into the local variable pool, but except you avoid the wide modifier by just simply saying that the index is 2 bytes long. So yeah, you don't need many different stores because it's fixed with elements, and so type checking on storage and loading, it's all just done with the verifier, and then we can just do everything naively. Next, objects. so there's I think 2 slides on this one. We have new, right? We can't get rid of new. Get field, get static, put field, and put static. So the reason we have these 4 still is because the way classes are and objects are kind of stored is different enough that we don't. It just seemed too hard to try to merge into just get and put. So we just leave it with the exact same way that the Java implementation has it. Invoke. So the same idea here. So we have invoke and invoke static, but we kind of figured we can get rid of invoke interface and invoke special because we can verify interface types again through the verifier. So invoking through an interface doesn't really need to be checked. It's really just another method implemented as part of the class. So it's almost like when you actually run the code, interfaces don't really exist anymore. And with invoke special, it was used for 3 situations: data hiding, so private methods, constructors, and superclass calls. But all of these can kind of, so the data hiding can be statically checked, and then you can, so you actually do need to do a dynamic lookup, which is a performance cost, but I mean, you have less bytecodes, which is the goal. So constructors can be just normal virtual method calls and superclass calls that you can just look at the superclass and make another normal virtual call. And invoke static is necessary for the same reason as before, and we left invoke dynamic because it was a necessary optimization for. I read about what dynamic languages previously had to do to work on the JVM, and I just felt pity, so I put that back in. And finally, arrays. Arrays also two differently implemented to be handled as like just treat it like an object, right? So we have new array, array length, a load, a store. So technically in the bytecode, you can have any type of object in your array. So it's not basically the verifier has to make sure that the types are fine, but that way we can just blindly load and store anything into the array. And yeah, that's the whole bytecode set. It's 48 instructions.
Questions?
Why didn't you just get rid of void and make all your void methods into like integers?
Wait, so what do you mean by that?
I mean, you could just make all your void methods return 0 and just be an integer type, like C, and then just not have a void type.
Yeah, that's true. I mean, it's just felt a little cleaner. I mean, it also rounded it off to 48 instead of 47. There's just we could have done something like that if we wanted to eliminate that one.
Table switch?
Oh, so basically we just said, table switch and lookup switch are useful for like performance, but you can if you want to get rid of them, you can just simply do a bunch of if statements, right? So I mean, yeah, it's just another decision. We want to go minimal. Performance cost isn't that important to us, but I mean, adding those two wouldn't be such a huge cost because it doesn't make a huge effect on other things. It would just be 2 extra instructions for like some more performance.
I may have missed it. Was there a throw instruction over there?
Oh, I guess I forgot to write it down. There was originally a throw instruction. I can show you my notes in my notebook. Yes,
So
there is a
a throw anymore, or there is it?
There is a throw, and
Okay.
it's untyped. Yeah,
Oh, okay.
there's a throw, and it's just untyped in the same way.
So in your opinion, is dupe and swap really necessary? It's feeding got by without them, right?
Yeah, I was thinking about that. I mean, I was thinking about whether you needed all of those things at all, but I didn't look deeply enough into it. And I just kind of figured, well, I guess there's good enough use cases for dupe to X1 for someone to have like gone through the trouble to implement it. So I might as well just have a way to do the same thing, right? But yeah, it's probably could do without them.
So just comment on that. I've seen dupe being used heavily, at least for object constructors in Java. Usually there's a new followed by a dupe and then a constructor call, so that the constructor is called and yet you still have a reference on the stack. And if you were to not have a dupe, you would probably have to store it in a local variable slot. So if you had an expression where there were constructors which were not assigned to any variable, you would then necessarily have to make space for those in local variable slots if you didn't have dupes. So I think maybe that's the reason why.
Okay.
JVM.
So I didn't quite follow how super was going to work.
Yeah, that's one of the things I kind of hand waved a little bit.
Okay.
Well, I was thinking there probably would have to be an invoke super because that was the case that kind of got me.
I don't think you can handle that by the generic invoke.
Yeah, probably not.
Yeah.
Unless
you have
don't
like
know,
a boolean saying it's super or not.
Right, exactly. Yeah. So just add another like byte.
Right.
Yeah.
Just stick it in dynamic.
Make it part of dynamic.
Okay. Okay. Thank you.
Thank you.
Thank you. So this was actually pretty representative of many of the presentations in bringing up sort of similar kinds of things. I was mainly looking for the realization the type stuff could be exploited in the verifier to generate the information that's redundant in the bytecodes, and I think most people got that. One or two people talked about the cost overhead of doing that in the interpreter. Anyone see a way of removing the type information from the bytecodes but still having the interpreter be fast? Don't think anyone actually had a solution.
Well, I mean, if you do JIT compilation, you sort of do like abstract interpretation to like determine the types, and then emit the proper code with.
Right. So you can basically translate the bytecode into typed bytecode if you wanted to interpret typed bytecode.
You can also use some of the bits that are left over. Like
Yeah. Exactly. Okay.
Possibly caching.
Yeah.
So once you know what it is.
Yeah. And then I think most people had some alternate arrangement of the stack to avoid the weird schizophrenia that the JVM stack has. The other one I saw in a couple of presentations, which I thought was a good one, was basically, whatever's on the stack is on the top of the stack and the item sizes are not specified. It's like the implementation has to figure it out how big the thing is and it gets to decide. So making it sort of uniformly big is one way, and just saying, punting on the exact space requirements is also, I think, a fine way to go. Let's see, we had the Nathan and whoever the other guy was presentation. You had some interesting monitor changes.
Oh, yeah, that was.
Yeah, so summarize your proposed
so the
monitor.
thing is like basically the unlock monitor, it references the instruction of
Okay.
the lock monitor, so that way, because when you do the unlock, you're still doing a lot of type check, like checking like,
Right.
does this thread own it, have I done it multiple times, and if you could like statically do it, because you could just check the code tab.
Okay, so you're basically checking for nesting of the
Yeah.
pairs. Right.
And
static
like,
line.
I think one thing is like, currently you could just pass like any object into like the unlock,
Yeah.
or at least in the bytecode sense. And,
Right.
that doesn't really make sense. I don't know of any language on the JVM that would like make use of
Right.
some weird
Right,
thing
the
like that.
unstructured one. Yeah, okay. And then the other idea I thought that was interesting was merging the gets and the puts all into like a generic get and put bytecode, and using the information in the descriptors in the constant pool to distinguish between the various cases. And you can sort of push the information around semi-arbitrarily to wherever you want it. It all depends what you're trying to accomplish. Okay, now the other presentation I wanted to see was the one that's very different than everybody else's.
Extreme minimal.
This is just
Just
It's actually not minimal, but it's minimal.
so someone
You're standing up too, so.
walk us through the idea. You don't have to give us, the
Yeah.
huge details. Just walk us through the basic idea, because this is very different.
I'm extremely tired, so hopefully I will be semi-coherent. Speaking of pushing data wherever we want, so there's a proof recently. There's actually a single Intel instruction that is Turing complete. We did not do that. We did close. We did 3 instructions. So the lambda calculus allows you to be Turing complete with just invoke. We put go to if null because why increase the stack frame when you can just stay in the current stack frame? And then we have CLOAD, which is basically the transfer between stack information, constant, method name, so on, into our dynamic context. So if we want to do function, I did just before. The constant pool then has to have reference to the stuff that we know is going to exist, which is the stack, the call frame, operand stack. native methods, so yeah, those. If know they exist, you know they exist during runtime, so you put them in constant pools by some reference. So you can load them and then go to them. Yeah, so the bytecode is extremely unrestricted, less so than even lambda calculus, and calculus is restricted by comparison. So, fun stuff. Let me jump through that. We do not
So what you're doing is basically you're putting the names of all of the things that you need to get to as symbols in the constant pool.
Yes.
And you're sort of intrinsifying all of those operations and then just calculating using those intrinsified operations.
Verification is no longer in any way, shape, or form logically possible. Everything on the stack is a pointer. So integer objects are a pointer to a tag and value. Floating point be similar, so on and so forth. Though you could obviously implement it other ways. Cload, you give it an identifier in the constant pool, it loads it. When I say constant pool, I mean pool items. It's a pool of items that we know exist via static information. The objects there can point to things that change, so it's a const pointer, not a pointer const. Scheme. Theisms, I feel like I just skipped right to the example. Go to if null, so it takes the top of the operand stack. If it's null, it goes to label. Label is just offset. Invoke is the fun part. So we have 2 arguments, so we could have made it 3 to make it a little more logical. Invoke is always a method call, so the receiver object is always on the stack, and then you also have the method index is also on the stack, operand stack, though we could have made that static, but then we can't support some cool things. Argument numbers, how many other things you need to pop up the stack, and then we have exception table, which is should exception be thrown, which is called by a method on the stack object. It looks up the exception table and calls a function there, invokes a function there. Yeah, do you have any questions? Everything's invoke. The example will probably hopefully make things more clear. So yeah, do you want to
Yeah. Okay. So so this is an example. So since we only have 3 instructions, so we will simulate all the other JVM instructions by just using these 3 instructions. So this is an example we simulate A0. We will first load the call stack from the constant pool, then we will load the throw instructions pointer to the native function, and we'll invoke it. So yeah, this is an example. This is the constant pool, this is the operand stack, and that's the instruction pointer. And so when we first when we execute the first instruction, we'll first load the call stack from the constant pool. Then we'll load the instructions pointer into the constant pool. Then we'll invoke that as a native function. We'll first pop out the call stack as the receiver object. Then it will pop out 1 argument as the argument to the native function call, and we'll invoke it. Yeah. Okay. So so here are some other thoughts. So basically, because in our bytecode design, the bytecode can operate on any metadata structures. So the load and store can actually be simulated by put field and get field on the frame object, and the put field and get field can be simulated by invoke. And
this trickles all the way down.
Yeah, this is another example. Simulate A equals B plus A. So this first block simulates load A from the local frame, and we will first load the A's local index. Then we will load the call stack frame. Then we will load the get field operation. Then we will invoke it. And then similarly for loading B, and then add up, we just load the add instruction, then invoke it. Finally store B.
Okay. Questions? Comments? Rotten fruit.
So let me preface before I answer questions. We went with the orthogonal instructions. We just took that and ran. So, and we can be more orthogonal. We can get rid of go to if null, and actually that's as far as I'm willing to go. Did you have a question?
I had this other one sort of weird question. Suppose if you ignored operands for a second, and you just assigned 1 bit or 2 bits to each one of these instructions, how did it compare in optical size.
I feel like you would actually have a blow up because the instruction set. You should have a blow up. I feel like the information, the entropy there is that you have a blow up, but it'd be cool to see how it actually works. Any questions, comments, observations? This is a horrible, but our restraints were very thin, so our result is very extreme.
Cool, thank you. Have either of you programmed in Forth?
I've read Forth.
Oh, okay. Was that a conscious influence?
No.
Yeah.
That was way too long ago, I think. Oh.
Okay, so just a couple of other sort of discussion points. So why in general would you redo the bytecode set in Java? Anyone think of good ideas, good reasons for why you might want to redesign it? What would you get out of it?
It would make it easier for people to write alternative language front ends.
Yeah,
You wouldn't have
that's a good
enormous-
reason.
Like you wouldn't have to read through a manual this thing to figure out how to generate the proper code.
Okay. So users of the system would have an easier time, in effect, the people who are the clients of the bytecode. Yeah. So
One interesting constraint is if you can have a dynamic language interface correctly with original Java bytecode without having some special magical handling.
Mhm. Okay.
Which would require modifying the constant pool if I remember correctly.
If the bytecode, if the instruction set's easier to reason about, then it's easier to JIT over.
Maybe.
So you can be more clever in your interpreter. It's sort of the risk argument in ISA.
Yeah.
That you can have if your compiler is clever enough, you may as well just have simple things.
Yeah.
because your compiler
Yeah,
can
so
get
that I buy. In general, one of the things I've observed is that there's a lot of code in a complex VM which is just dealing with the particular encoding that's present. So you get that switch statement, across all the bytecode types and a loop around it doing abstract interpretation many times, right? And just reducing the size of that reduces the maintenance burden on the VM considerably. If you can do that and not pay for it in some other way, then in general simplifying that is a win. So that's another good reason. What about the size of the compiled programs, in the bytecode format? Is that important?
When? What year is it?
Yeah.
We are pushing on CPU bandwidth at this point, but I'm not sure how big.
Of the bytecode set, not of the generated code, but the stuff that you get, the equivalent of what's in a .class file.
Larger is worse for analysis, but I'm not sure how much of an issue that is for people who aren't doing if you're working in the JVM, you only care about the JVM, I'm not sure how much of an issue that is when we try to do an alternate JVM.
And there's been a lot of work done to shrink the size of the files down, because it turns out that actually shipping the jar files around containing all this stuff is a significant barrier to uptake in some questions. But the open question is the right way to do that by bytecode design or just putting a compressor on the transmission medium, right? And decompressing when you get to the end, and who cares about what the size of the file is on the disk?
So how big do these things get? I mean, I've never gone around, ls-sing the jar files.
Well,
typical Java application minus the
megabytes is very common, and tens of megabytes is not unusual, right? I mean,
how about for the hot code?
Those are tiny, typically.
Those I thought jar files were zipped files. I had compression around them.
Yeah, exactly.
Well,
exactly. So if you're gzipping anywhere, does it really matter how densely encoded this is? Because it's not what you're going to run, and it's not going to be what you distribute, right? The entropy is going to be removed by the compressor.
Typically, when I see a jar file and it's big, it's the assets or
Yeah,
it's,
right,
Java
exactly,
files.
exactly.
See, this was designed in the 90s.
Yeah, and the context of the design is important, because the context of the design was that they were going to put this implementation in set-top boxes and remote controls, because this was pre-web, right? This was before people appreciated that the internet was going to be the distribution mechanism for content, executable content. They thought the cable TV system was going to be that medium. And they were going to put interpreters in set-top boxes and in smart remote controls, which are obviously, in 1991, enormously space constrained.
So the design assumptions have changed radically.
Absolutely.
And Gosling had this great line in this paper. He talked about reducing the tyranny of the instruction set.
Mm-hmm.
And now we have this instruction set that has lived since.
Yeah. I did a back-of-the-envelope calculation a while ago to get some sense of how much implementation effort has gone into Hotspot. And I think it's somewhere on the order of 300 to 500 person years has gone into it. And I would guess fully 25% of that is due to that bytecode set. Just dealing with the ins and outs and the complexities. And if you'd have picked a simpler one, it would have been a lot easier. Yeah, if you think full employment for virtual machinists is a good thing, then maybe you don't mind about that. But it is a very complex thing. Okay. I think that was all I wanted to say about that. Any questions before we move on, or comments? Let's make a start on memory management then. Okay. So this is going to drag out over probably several sessions, although I'm going to omit the more esoteric parts until very late. Depending on what schedule pressures, we may or may not get to concurrent and parallel collection. But I'm going to cover the basics of serial collection now and next week for sure. There are two, unlike the rest of the course, there are two really, really good books in this area, both by the same guy, basically. Richard Jones wrote this one in the mid-90s with his co-author basically just contributed one section. So it's mainly Richard Jones's book. And then it got updated a few years ago with a couple of good co-authors who reorganized the text and added new material. Because in the interval, sort of, the first one was written just as Java appeared, and Java spawned just a massive amount of work on GC. And so a lot of the papers in the intervening 10 years are nicely summarized, and this is the book itself. And I have two copies because I did a review for the publisher, so one of them is the prize for the fastest implementation. Feeney, and you're not eligible.
Does that book replace the first one?
Not entirely. As a practical handbook, it does, if you're looking for things that you want to implement. As a work of scholarly description, it doesn't, because the first book describes a whole bunch of things that were in the literature, but that really never won. They're sort of interesting if your object of study is GC, but they're not things that you're actually going to put into an implementation.
Okay.
So this is the one to start with. This is the one that has all the good stuff in, and occasionally, you'll find other techniques, or it'll even cross-reference. It'll say, and there's this other obscure thing, and go read the other book if you want to learn about that. Okay, so let's start from the very beginning, which is, why do automatic memory management at all? You could do static allocation, right? You can have names bound to locations, done at compile time or link time. The size of everything is fixed, there's no stack, and that really works. People have written real programs using that. Once upon a time, all programs were written like this, and it's still used in the embedded and real-time world quite heavily, because if you don't do this stuff, you don't pay for it. There's no cost at runtime for doing all of the management of a stack or allocation of GC or freeing or whatever. But more importantly, you can't fail because you run out of memory. Right? You've decided up ahead of time exactly how much you need to run your program correctly, and that's what you use. And you're not going to run out of memory at runtime. I tell you one funny story, which is when I was learning to code back in high school, we used to write programs in BASIC. And the BASIC system used this technique. It was like Fortran in that every subroutine had a link address allocated in the compiled arena for the return code. of course, I didn't know any of that because I was just a beginning basic programmer. But halfway through the course, I picked up a book on algol and read about recursion and thought, oh, this is cool. And tried it. Unfortunately, or fortunately, depending on which way you look at it, when I went to the next time to the computer center, back then we handed in sheets of paper with our program written out, and they gave us back the listing of what happened when it ran. When I went back to pick it up, I got a line printer output that was about 2 inches thick instead of the usual, 3 pages, because the recursion I'd written had overwritten the return address, the link return address, and the thing had core dumped. So I got 200 pages of octal dump with a note from the programmer in charge of that mainframe saying, "Come and see me," and he explained what happened. He'd had to wade through the core dump to figure out what happened and said, "Don't do that again." But when back then paper was in scarce supply, it lasted me years, that listing. So it's it used to be done like this all the time. In fact, if it still is done in the real-time world. If you want to have a hair-raising experience, go find the expert witness testimony in the Toyota trial of 2 or 3 years ago, where there was this thing where there were unintended accelerations in Priuses and other cars, and an expert was brought in to look at the code, and they found things like recursion in the source code of the controller for the engine management system, right? Which, stack overflow in your car, not a good idea. So, worth knowing about the alternative, but it's not been widespread use by any stretch. So the downsides, there are numerous ones, mainly in that life is just difficult as a programmer when you have to live with static allocation. You have to do all of your calculations for the worst case up front and maximally sized structures, and you can't change the subdivisions dynamically. So if you're in an environment where you can do any kind of time sharing or resource sharing, this is not going to be good, because it sort of grabs everything and keeps it all the time. So fixed subdivisions can't adapt, you can't use the recursion. You can still do it in things like the Java real-time spec. There's a sort of you can write real-time critical sections in Java, and if you do that, you can only use static allocation in those parts to avoid this problem. So you're punting the dynamic behavior to the non-critical part of the program, and if that fails, no big deal, that part of the system gets restarted, but the critical part keeps running. Okay, and I think I answered the question myself. Dynamic allocation in stack. You're all familiar with stack-based routines. Mostly follow a LIFO principle. As you saw last week in Smalltalk systems, some don't. Some follow a non-LIFO discipline, and so you have to deal with heap allocation of stack frames in some form or another. But if they don't, you can most easily do things as a stack, and processors have acknowledged the presence of a stack by adding in things like hardware stack pointers in the 60s. And so all life is good. If you don't have LIFO activations, then life is difficult, and you have to do some amount of fiddling about with the stack and copying. So continuations in scheme, you have to do this, Smalltalk the activation records, potentially first-class objects, and it all implies that things are heap allocated, which will make you scream. But as you saw last week, there are tricks to get around that. I'm not going to go into the detail here because these languages are still pretty much in the minority, and the chance that you haven't implement this in a high-performance way is probably remote. And if you have, you've got many more problems than this. So mainly, we're going to be talking about the heap. So the heap is arbitrary memory pool. The program can make requests of any size in any order, and the pool has to give back chunks of memory in the sizes that were asked for. And if you can't give back a chunk, you say, sorry, but I can't give you back a chunk. And then you've got either the language or the programmer has to decide what happens in those cases. The programmer either gets to do something and behave differently, or the system just stops dead in its tracks at that point. Either of those, it's all dependent on the semantics of the system. But usually you're making your best effort to give back the memory that it's asked for. The pool can consist of many separate contiguous areas, right? It used to be that, memory was this linear thing, it was not virtual. You just got a big chunk of it and you allocate it out of the chunk. These days, the way you get memory in OS-based systems is you call down to the OS and it gives you a chunk of mapped virtual memory back, and it might not be contiguous with the last chunk it gave you. You have to deal with discontinuities in the heap. But that doesn't usually make for much of a problem. The only situation in which that really causes a problem if somebody asks for a piece that's so big that none of the individual pieces can satisfy it, but yeah, that's very rare and unlikely. So your first order problems really are allocating and deallocating. That's the thing that's most common. That's what you've got to get right first. So let's look at allocation. The classic technique is to use a free list. So here are all your free cells. They're of different sizes. They're linked together in a list. When a request comes in, you have a number of choices of how to satisfy it. You can pick the first thing that satisfies it. So that's just, you walk along the list, and as soon as you find a piece that's big enough, that's the one you're going to give back. What you have to do is split that chunk in two, if it's too big, and thread the remaining piece onto the list. Very simple, straightforward, no difficulty there. There are many other scheme variants on the scheme. Best fit is another common variant, and best fit means if you find a size that's the exact right size, a chunk that's the exact right size, give that back. Otherwise, give back the next biggest one that you found. So in this case, there are none that are the exact right size. That's the closest fit. It's just a little bit too big, and so you chop off the tail and add that to the list. Now, you can come up with some interesting redefinitions of best here, because the problem with doing it in this way is that you end up with an awful lot of small pieces that are mostly useless. Best can be the opposite extreme, right? The biggest. Get the biggest piece and chop that up. So there's a number of variations on these, and you have to figure out sort of which one is appropriate in your system. I'm not going to go through all of this in a lot of detail because it turns out this is the wrong way anyway. We'll get on to better ways. So you can keep these things off to the side. You can have special lists of useless pieces. You can do all sorts of techniques. You can round up the size of a request. Suppose this is only one word and your minimum object size is 2 words. Well, this one word thing is useless, right? You can't do anything with it. So you're either going to keep it off to the side. You don't want it on the free list because you're going to have to traverse it every time you look down the list. You might keep it off to the side as a separate list of chunks, or you might just round up the request and then keep an extra word with this object. That's also a common technique. Yes?
Do they keep all this in a sorted list to do this? Or
No, not usually. Sorting is not considered cheap enough, typically. So they usually the list gets really chaotic after time if you've got a single free list, because the requests sort of break it up into pieces, and the distribution of sizes gets sort of random.
Okay, so best is approximately best.
Yeah, well, if it's the same, then it's best.
Right.
And then what you can do is go down the list and keep the smallest thing that was bigger and use that. That's a common best fit technique. These are all, by the way, things that are typically done in malloc. And malloc is really slow by comparison to what we're going to do. Okay, so there's the next fit is another common technique, and that's in next fit what you do is imagine that we started with a list and we were allocating from the front of it. As you allocate from the front, you're chopping up the big pieces at the front, and you end up with a lot of small things at the front of the list. Often those things are so small they're not really useful for much. They might be useful for something, but they're not dynamic. The frequency of their usefulness is not very high, and so rather than traversing that prefix of the list that contains a bunch of useless stuff, what you can do is remember the last place you got a block and start there. And to do that, you need to make it, instead of a list, into a cycle, a queue. So in this case, what we do is when we split this into 2, we next start the search from this point. And we go round and round the cycle looking for things. Obviously, you need another pointer in your hands to figure out when you've gone once round and come back to the beginning. Because you don't have the null pointer into the list to do that. But this is another fairly common technique. So, unfortunately, this is all slow. To implement it, you need a loop. The number of iterations in the loop can be large because you're working down this list. It could be going for a long time. You need a size test because you know how big a piece you want, but you don't know why big a piece is coming next on the list. And you need to be able to split up a block. And by the time you combine the logic for all of those into one thing, there's no fast path. You can't inline that whole thing at every allocation site, which is really what you want to do. It's just too big. So you don't want to do this as your basic technique. So how do we deal with this? Well, I haven't talked about the distribution of the sizes in the system, either the requested sizes or the allocated sizes. And obviously that depends on the program. But it's heavily influenced by the language, the style in which the language is used and the available libraries. If all the data structures in your program are coming out of a library, then the sizes are going to be dictated by the library. If it's the standard library that goes with the language for everyone, then everybody's program is probably going to have objects of sizes dictated by those libraries. So you end up with very skewed distributions of sizes. So examples, you're on Lisp, then there's going to be a lot of two-element consoles around there. It's just the language, that's the way you do stuff in Lisp, and so you're going to see a lot of those. As I said earlier, in object-oriented languages, most requests are for small objects. 2 to 10 fields is the common size. Very rare that you see stuff much smaller than that, 1 field. 0 fields, sometimes there are 0 field objects, but they're not very common. And it's very rare that you see stuff with more than 10 named fields, because programmers just can't carry that many names in their head when they're writing programs, right? There's this old psychology result that says you can remember, on average, about 7 things in short-term memory, and so that's how people write their programs. They push the other stuff off into sub-objects or into superclasses and abstract over it. That's why we have abstraction mechanisms. So that dictates demographics a lot. And the only exception to that typically is arrays, which, there the abstraction is the index, and so it doesn't make the programmer's life any harder as to whether it's got 10 elements or 1 million, if they're all treated the same way. So you tend to get this very bimodal distribution of sizes, a very large number of small objects, and a few large objects that contain the arrays and the other data structures. And we don't have optimizations for coalescing objects that are really effective. There's been some amount of work done in trying to figure out in a compiler how to take a graph of objects as described by the programmer and glom a bunch into a bigger object and manipulate that. But none of those things have turned out to be really practical. We don't have them in VMs. Maybe if someone's looking for a PhD topic, there's a good way to go. If you can make your name by figuring out how to coalesce objects at runtime. And that then would change the assumptions underlying GC fairly dramatically, and we'd have to revisit all this stuff again with different techniques. So one of the things we can do, if most objects are small, is deal with the small objects with specific cases and then sort of punt to a free list for only the big stuff. So for the small objects, we can have a free list per size, right? So the one field object, which is typically 3 words because there's a header, can have its own free list, etc. for 2 fields, 3 fields, etc. And that eliminates the size check, because now everything in the list is the same size. We know the thing on the front of the list is the right size, by definition. It eliminates the splitting of objects in the fast path, because you go down this list and they're all the right size. You only need a general free list for the large stuff, and for when the smaller free lists exhaust space. So if you end up with a small free list that's empty, you look down the thing and there's nothing there, well, you take a bigger chunk and you chop it into pieces and populate your free list. And this is a very common technique. It's used a lot and sort of look graphically as you might expect. So you take these guys, which are the free list heads, and you stick them in an array, and then you index using the size of the thing that you're trying to look up. And if you'll need, typically at the allocation point, you'll either know the size, because it's an instance of a class, and so those things are compile time size known, or you're allocating an array, in which case it could be any size, and you're going down this list anyway. So typically at the allocation site, you'll know which list head you're concerned with, and so you can compile that in and start basically it's a simple test to see if it's null. If it's not null, pull the front thing off the front, and you're done. So this is sort of the best you'll get with free lists, typically. Constant time lookup in the common case. Now, the demon in all of this, in managing stuff via free lists, is fragmentation. So as free memory gets chopped up into smaller and smaller pieces, it fragments. And then you get the problem that you want a big piece. Say somebody asks for a bigger array or an object that's not allocated very commonly, and there's tons of free memory, but there isn't a piece that's big enough to hold the thing that you've got. And now life is bad, because you have to somehow reorganize the system to coalesce things, or you just say, sorry, we're dead, program is over, restart. Which is what is the common case, right? In C, that's what happens. You call malloc. If malloc gives you back 0 because it can't find a space, you don't call a garbage collector because there isn't one. You die. So this is common and painful, and you'd rather not go there if you can. Now there are two types of fragmentation. The one that I mentioned earlier, where you over-allocate because you have some constraints on your allocation sizes. And this is more common in some kinds of allocation schemes where, for example, all your allocation sizes are powers of 2, the so-called buddy system. That's common in operating systems for page size things, but it's not common in language implementations. So you might get a little bit of internal fragmentation. Another cause of this is alignment things. Say you're on a 64-bit system, and you want every object to begin on a 64-bit boundary. Well, they're not all exactly multiples of 8 bytes long. There'll be bools and shorts and stuff in there, and so you might have to pad a little bit at the end. And that'll give you some internal fragmentation. But the more serious problem tends to be, or at least the more solvable problem tends to be external fragmentation, which is the fact that you've got many small free blocks, but no big ones. And we'll deal with that with collections, so we'll get there in the end. Now, how fast does the allocator need to be? Is this important? And actually it is. In any object-oriented language, objects are common, so allocation is frequent. Allocation is happening all the time. Now, it's worth remembering that initialization is typically linear in the object size. The bigger you make the object, the more it's going to cost you to zero it out or set it up before it can be used. And so the pressure is to making the small objects cheap to make, as close to free as you possibly can. So very light costs for allocation and very efficient reclamation when it comes to recycling that memory too. So that's the pressure. The large objects, if somebody asks for a 1,000,000 element array, they're not going to expect that to be ready 2 cycles later. Right? You have to allocate all the space and fill it out, and they're probably going to fill it with some data. Who knows where that's coming from, but that might require some I/O. It's the small stuff that you really want to make fast. And there's a more general point which is worth bringing out here, which is that objects are a kind of abstraction in programming languages, just as methods or functions are. And it's a good goal, a really good goal, to try and make abstractions as cheap to execute as possible. Right? The more you can reduce the cost of an abstraction, the more people are likely to factor their programs in good ways and shape them and divide them up. And so sort of our goal as VM implementers is to try and make abstractions really cheap. You'll see when we cover the compilation stuff that practically you can make method calls as close to free as makes no difference by the inlining techniques. That's an achievable goal. This is much harder. No one has got this down to 0, not even close, but it can be made reasonably cheap. And the cheapest technique for allocation is bump allocation. And the setup for bump allocation is we have a big contiguous region of memory. We start allocating from one end, and we keep a pointer that says we've allocated up to this far. And when a request comes in, we do the easy thing. We bump the size up for the requested piece, and we're done. And the only other thing we need to do is check if we fell off the end. It's very cheap. It's very fast. The code looks something like that, which is definitely something that you could put in line at every allocation site. Okay, so we have P is the thing we're going to give back. Free is our free pointer, and end is the end of our free block. We increment free by the size of the thing we want to give back. If that's going to fit within the region, we just bump the free pointer up and return the thing that it used to point to. It's very simple and fast. But you may ask, did we cheat? I mean, hold on, what's the setup here? What happens when this thing fills, right? And we free stuff up, and aren't we going to just degenerate back to a free list? Is it like a one-shot thing for one iteration of the heap? You get cheap allocation, and then after that it's all free lists. No. But to get to the end point, we have to go through this circuitous detour through some other techniques of garbage collection, because it's not straightforward to explain all in one go. So the target will be a compacting garbage collection, which basically starts with a heap that looks like that with everything at one end, and when it's done, after you've allocated the GC, it looks like that again. That's the end point, the cyclic state. But we'll look at some others in between. Okay, so the complement of allocation is deallocation. So, if the language says the programmer does that, hooray, we're done. Great, it's their problem. But alas, it probably isn't going to be your problem. Why is it, what are the advantages of garbage collection? Why do people put it in? Why do they push the burden onto the programmer?
Programmers don't have to think about it.
Yeah, it's worse than that, right? Even when they have to think about it, they get it wrong. And when they get it wrong, really bad stuff happens. So it eliminates, main reason is that it eliminates a class of unsafe errors. And the unsafe error is you free the thing that a pointer is pointing to, and you use that memory for something else, but you keep using the old pointer as if the old thing was still there, right? And that's bad stuff happens because no one detects when that happens, and your program is incorrect, but you don't know it until sometime later, when either your bank balance goes to zero or you get a segmentation fault or something like that, right? It's a really, really nasty class of error, because it's not the triggering of the error behavior doesn't result in a flag saying something bad happened. That happens much later, if you're lucky. Maybe not at all. Maybe you just get corrupted data. Yes?
Is there any system, or is it even possible to have explicit deallocation but still have bump allocation?
Explicit deallocation and bump allocation. I have to think about that.
I mean,
ask that.
You do it internally in C all the time. So like, I've written lots and lots and lots of things in C where we write a stack allocator. We call it a stack allocator, but it's the same thing. And you just allocate, you ask malloc to give you like a megabyte, right?
Oh, so you do internal allocation from your own region. Yeah, sure.
Yeah, and then you give it to like a sub module, right? So like I invoke some sub thing, a function or like something more complicated like we were talking about earlier. Yeah. And you just give it a megabyte of memory, and then when it's done, you just free the whole thing. And so
so that's region-based
it's
collection.
Like your,
so you give a chunk of memory, and so within, say, the scope of a function, it has a chunk of memory which it can bump allocate, but when the function returns, it just gives it all back because it doesn't need it anymore. But that's probably not what you were thinking.
That's not what I was thinking.
Yeah, I mean, the most general case I think I have to think about.
So Philip Reams wrote this paper about hinted garbage collection, which where deallocation instructions become hint for conventional garbage collection. So that one is, I think,
I see. Okay,
it's kind of
interesting.
Yeah.
It might be a hint just to run the garbage collector. No.
If I can get Peter Kessler in. Peter was the implementer of a lot of the garbage collection stuff in Hotspot. And the bane of his existence is system.gc, which is the Java entry point that says, do a garbage collection for me, because it's like programmers never ever know when to call that properly. They always make things worse. So, the other really good reason for doing this is if your program is written by more than one person and you're composing things together, if you have to compose stuff with memory management and explicit deallocation, you have to come up with some really good discipline or regime for who's going to do that. Because when you put stuff together, someone better be in charge of each individual cell and know when it's going to be deallocated. And that's like the bane of really large systems programming using explicit deallocation, is kind of figuring out the rules by which everybody operates and enforcing them in a way that's acceptable. You had a question?
Well, so what do you mean by explicit deallocation?
So the programmer says, I'm done with this, you can free it.
Literally, so like Rust, for instance, is not a garbage collected language, but it has safe pointers because it's all statically checked. Would you consider that explicitly deallocated languages?
Meaning what by safe pointers because they're statically checked? Isn't there do you need to like solve the halting problem?
No, you don't, because it just restricts the use of pointers to be only in certain cases. So if you're familiar with C++ unique pointer, so it's basically all pointers are unique pointers, except, in Rust all pointers are unique pointers. So it's a static property that's able to check. Would you consider that a...
It's like an ownership thing.
Yeah, it's literally ownership by the language. Is that a explicitly deallocated?
If you can figure it out ahead of time, then yes. Even if it's not coming from a programmer, but you can derive it from the type information, I would consider that explicit deallocation. And in fact, one of the goals of some compiler optimizations, even in languages in which you can't do it in general, is to figure out some specific cases where the compiler can say, oh, I know now that this thing is free, and tell the system to free it up. But most languages, it's like either one or the other. You either get explicit deallocation or you get automatic memory management, and then sort of the burden is on the implementer to deal with the automatic system. Okay. The one thing, of course, this doesn't prevent is memory leaks, right? Because you can still build structures that you're not going to use and have them referenced in a way that the garbage collector can't figure out that you're not going to use them. So it's not a cure-all by any means. Okay, here's a little quiz for you. Here's a little Java program, excuse me. Here's the main, this is the whole program minus the junk at the sides, and I elided a try-catch which you needed here to make it run. So I'm taking in the argument strings, I'm going to read the name of one as a file, read the whole thing into a list of strings, and then I'm going to count how many lines are in that file and print it out. Can I reclaim this data structure, which is the list of strings, right here just before the print line? I'll give you 15 seconds to think about it, and then I'll take a show of hands.
Isn't it reading the program file?
Isn't it what?
Isn't it reading? I mean, as presumably 0 is the file.
No, 0 is the
binary.
first argument. You don't. Java doesn't give you the name of the binary. This is just a random file. Okay, who thinks I can reclaim this data structure at this point before the print statement? Hands. 1, 2, 3, 4, 5, 6, 7, 8. Who thinks I can't?
I'm going to be safe to say you can't.
Okay. Why do you think I can't?
Well, it would be too easy.
I'm an extremely conservative garbage collector.
Well, so
you can clean it very once it goes out of scope.
actually, sure you can. In this specific example, sure you can, because it's not used, right? The whole point, things are reclaimable when they're no longer going to be used. So an ideal definition is that an object's dead when it's no longer needed. The unfortunate part is the system has a very limited crystal ball looking into the future to figure out whether it's going to be needed or not. Now, the programmer might know that, and that's why you can do free. In fact, you have to be able to know that to do free, because to call free, you have to have a pointer to the thing, right? Which means after you've called free, chances are you can still access the thing. So it's The programmer knows this, but the compiler usually, or the VM, usually can't figure this out. It can't figure out whether something's going to be used in the future or not. So instead, we use this other, weaker definition for all GC work, which is reachability from the roots. So the roots are typically the elements of the program that are declared, like the variables, the stuff that's on the stack, the globals, static, stuff like that. And if by following pointers from those you can get to an object, then there might be some way that it's going to be used in the future. You haven't got the ability to prove that it won't be used. But if you can't reach it, then for sure it's dead. Yes?
So you said that the system can't do it, but then we have this really intelligent system called the verifier. And you're saying that the verifier can't verify?
No. Halting problem again.
Okay.
In general, you can't do it. In specific examples, you can, but in general, you can't.
Well, okay, it can still fail to verify that it can dispose of this in.
If you can prove that it's not going to be needed, sure, you can remove it. So in a case like that example, a compiler could say, well, that variable's dead. There's no way that that thing can be removed. So I could, at this point, reclaim it. But it's a limited set of circumstances.
Limited is 99%.
No, in this case, it turns out to be
Okay.
very limited.
Very limited.
Very limited. If you only implemented compiler-style flow analysis and did only the reclamation that gave you, you'd run out of memory real quick.
So that's actually a question about hotspots. So would your compiler generate codes to remove, in this example, the list from a local slot in order to make it like based on lifetime analysis? Or?
No. The example where the compiler actually does something is typically in escape analysis, where it's trying to, in a body of code, prove that something that's being allocated can't escape that region. So it doesn't actually really have to allocate it at all. It's very rare that an example like that comes up, where the compiler can go, oh, yeah, I could remove this here, and it goes ahead. And it's sort of not so infrequent, it's not worth bothering.
But Martin?
Yeah.
So, but the compilers do often, they use liveness analysis to allocate many things that are not allowed to save time to the same stat slot.
Okay, so that's
So they override each other, but
Right.
Small.
You could have language semantics that said that once it can only be used once, so as soon as it's used.
Yeah, sure. Sure, functional languages get a lot of mileage from the fact that stuff isn't mutable. Yeah. Okay, so reachability. Here's a picture showing roots and a bunch of objects and a bunch of pointers. I'll take a quick look and try and figure out which ones are the live ones and which ones are the dead ones. Go on, shout out if you. Yeah, good. Let me remove it. Okay, so this one is. Did I get these in the right order? That one. These are all. These are all. Sorry, these are all dead. Okay, these are all dead. And the reason is, when you follow the pointers in the directions of the arrows out from the roots, those are the only ones you can get to. So if you look back at the earlier picture, there were ones pointing into this graph, but they don't count. They're not reachable from the roots. Okay, so let's start with probably the easiest and oldest memory management technique, which is reference counting. I'd be surprised if you don't know what this is already. So the idea is, with each object we maintain a reference count, which is the number of times the object is referred to. The way I think of it is the number of incoming arrowheads. Right, the other end of the arrow doesn't matter. It's the number of incoming arrowheads that you care about. And so when you copy one of those, you increment the count. When you destroy one of those references, you decrement the count. And if the count falls to 0, well, then nothing is pointing into it, and you can free the object, because if nothing is pointing into it, there's no way to get a pointer into it, unless you have a type unsafe language and you can do random casts of stuff, in which case none of this applies anyway. So in this particular case, there are the reference counts. I hope I got this right. So count the number of incoming arrows, and that's the reference count. Okay, so That 1 can be reclaimed because it's 0. And when we reclaim that, that destroys the pointer to A, which drops to 0, and so that one can be reclaimed. But we can't reclaim anything else, which is a problem. So how do you implement this? The easy thing is stick an integer field in your object. You build operations that do the counting up and the counting down. The count down has to test for 0 and do the free. And then the free has to call the countdown, right? So because when you free an object, you find all the references within it, and that you count those down. And then once you've gone through all of that process, this is recursive. So free is calling countdown is calling free object. Finally, at the end, you can actually free the memory. That's the simple implementation. However,
sorry, I got confused. When you decrease your reference count and then you remove this object, you have to follow the parent links?
you have to follow all of the outgoing pointers from that object and decrease their reference counts, because you're about to throw that object away.
It's a graph, not a tree.
Okay.
Should I run the animation again?
I think I just, no, it's fine. I don't want to do that.
Okay, so when something falls to 0, it becomes garbage, but all its pointers are about to be destroyed, and so the things that it points to have to have their references decremented.
Okay.
And they may fall to 0, and hence the recursion. That's what the recursion is doing here. Now, one downside of this is we're allocating an int here, and it's usually pretty wasteful to allocate a whole word for the count. Okay, so what's the maximum reference count you can get in the system? Well, if every word of memory points to one object at the end of memory, then sort of it's the number of words in your address space, right? Which is sort of typically a word-sized quantity. But it's very rare that anything like that's going to happen. Mostly, you end up building trees in which half of the leaves have got a reference count of 1. The leaves have a reference count of 1, and the interior nodes might be something more, or something like that. Reference counts are usually very small. There have been some empirical studies done of live systems that show, 1 is the most common, 2 is occasionally there, 3. A few objects are really popular, but most things are really small. So it's kind of wasteful to allocate a whole word for the count. So a common trick is to restrict the size of the count to a much smaller quantity, like 8 bits. But the problem there is, once you get to the maximum value of 8 bits, the next increment isn't going to increment beyond 255, it's going to stick at 255, and so now you can never decrement, because you don't know what the real count is. You just knew once it was at 255, and now it's just going to have to stick at that point. So that's called sticky reference counts, or saturated reference counts. It's very common, and it modifies your code like this. So before you do the increment, you have to test whether you've reached the maximum. When you do the decrement, you test whether you've reached the maximum, because you can't do anything if it's at the maximum count, otherwise you do what you did before. There's an interesting, clever little trick that's used to make that quicker, which is, suppose you're doing 8-bit reference counting. If you put the sticky bit at the least significant end, and not the most significant end, so basically when the number is odd, it's stuck, and when it's even, it's not stuck. Then you increment in 2s, and your decrement is easy because when it's stuck, decrementing by 2 leaves it stuck, and you don't have to test. So you've elided a test in this case. It was used commonly in Smalltalk systems. I don't know if Jonathan remembers this. I think Elliot came up with this one. Or at least I heard it from him.
Does x86 have a saturating I've seen a saturating add.
Maybe in SSE.
Well, but you need the test, right? It's got to tell you whether it's saturated, if it did. So it's got to be a saturated add with some flag being set.
I guess countdown would need the branch.
Yeah. So in use, we now have to rewrite some of our code. Some of it might be...
What happens to the sticky objects? They just stay around?
We'll get to that. We'll get to that. There's quite a stack of pending problems that this induces, which have to be resolved. Yes?
Couldn't you keep a second table somewhere that just sort of had all the overflow? You only needed to look up.
Yes, that's another way of doing it, but that costs... Then you have to put some more tests and logic in. Admittedly, the slow path and not the fast path, but yeah, you can do it that way. Yes, absolutely. And if you get the, the book has like infinite variations on reference. Okay, so so our one of the earlier ones, I don't remember which one now, had a couple of lines that looked like this, where we were pushing a value onto a stack and we were popping a value off the stack. You might think you can just get away by rewriting the pushes and the pops to do the reference counting. Can anyone see what the problem is if I just do that naively? This specific example might work, but in general, why can't I just like sprinkle the pushes and pops with increments and decrements and sort of leave it at that level? Well, so you end up with things like a reference being popped before it's pushed, and so the count falls to 0 in between. That can be a problem. You also have to deal with a situation where you copy a pointer onto itself. And so, if you decrement then increment, bad things will happen. So you can't, in general, just decorate some of the low-level stuff. In this case, I've rewritten the put to do things more directly. And one of the reasons is when I do this put here, because I'm doing a pop, in effect, the reference count of the thing on the top of the stack doesn't change because the reference moves from the top of the stack to this other location. It doesn't actually, increment anywhere. It's just a move of the thing. And so in that case, you don't want to do a decrement and an increment. You just want to optimize that pair away and save yourself the hassle. And that's what this slightly optimized version does. It only counts down the value that was the old top of stack. The old value of the variable that's being overwritten. So this is a common kind of thing, and you sprinkle these count ups and count downs in your code, and you debug it for weeks and weeks and weeks and weeks, trying to find out where you missed one or you put one in where it shouldn't belong, and eventually, hopefully, it works. Notice a common misconception here is we're copying references into the implementation languages variables. We don't count those too. The invariant here is that the references from the roots and the system objects are being counted, not the transient things in the implementation, because these are going to go, right? They're just artifacts of the implementation that we can't copy something without putting it somewhere else first. So otherwise you end up with this horrible knot where you're incrementing the counts, and then you have to increment the counts in the routine that increments the counts, and it doesn't end well. Okay, so a few little practicalities, and then next week we'll look at tracing collection. So in this straightforward implementation, you have to reference count everything, all of the variables in the language being implemented on the stack, the global variables in that language in the heap. And even when you return from a stack frame, right, if you have pointers in the stack frame, you have to decrement the references of the things being pointed to from that stack frame. So there's a lot of increments and decrements going on here. The basic thing is, you write an assignment, p equals q, and there's an increment and a decrement going on there. In fact, there's the increment of the thing, the q, and the decrement of what p used to point to. So there's a lot of extra side stuff going on here. If we're tagging, then we also have to layer the tagging code around this to make sure we're not trying to reference count ints because they don't point to anything. And you also have to deal with things like null pointers, which I've elided from this. So if you're doing reference counting, you don't know that you're not being passed a null pointer, and so you have to exclude nulls from being reference counted. Some systems also have certain objects which are critical to the operation of the system and must never be reclaimed. And so a common technique is that you assign those objects low-numbered addresses. So when your system boots up, you allocate those things and then remember the maximum address of the things you want to keep. And then a single test can elide those and null, because they're all less than a certain address. And if you arrange your tagging so that all the tagged variables are negative, so you put the tag bit at the high order end, then you can elide those two. So a single comparison eliminates all the tagged variables and null, and the system objects that you don't want to reclaim. And that's also a nice little trick for a reference counting system that avoids extra tests. Because this is happening so often, you really have to think about how this is implemented. You can, in a naive implementation, you spend 50% of your time just incrementing and decrementing counts. Another trick is that count up and count down are usually defined as macros rather than functions, because you don't want the function call overhead for those. Or if you're generating code, you generate them in line. And one of the reasons I wrote them as a pair, like this, instead of inlining this into here and having a single thing, is you could make this a macro, but if it was recursive, you couldn't. So you can macroize the fast path and just leave the slow path as a function call, because freeing is an infrequent activity relative to everything else. Yes?
If I'm implementing this, are there any like debugging consistency checks I can use to make sure? Like,
yes.
If I just forget one count, it seems impossible to check.
Well, so the main one is, we'll see next week, that because of the cycles, you need another collector as well.
Okay.
And the other collector can recompute the counts.
Oh, okay.
And when it recomputes them, it can check that the ones that were stored were the right ones.
I see.
That, unfortunately, doesn't tell you where the bug happened. It's just since the last GC you've got a count wrong. Because maintaining it globally and checking globally, well, unless you force a collection really often.
What about in the presence of saturation?
Yeah, so what it will do is it'll recompute the fact that the saturated thing should be saturated. So. Okay. Okay, so a couple of other things worth noting is when you decrement the count of an overwritten reference, you usually get a cache miss because you're decrementing something that you used to point to, but you don't point to anymore. That thing might not have been used for a long time, but you're going to the object and you're decrementing its count. So there's often a cache miss at that point. When you increment the count of a copied reference, you have to do a write to the object to increment its count, even if you're only reading the object. Right? The object might be shared across a whole bunch of things in read-only mode, but the counts are being incremented. So the implications here in a multiprocessor environment are not great, but you have other problems with race conditions in a multiprocessor environment, which we'll get to later. So making this concurrent is sort of a challenge to make it concurrent and reasonably efficient. Okay, there are a couple of practicalities around the freeing. Here's the freeing code. Can anyone see a possible sort of downside of this implementation? Think about what happens when I have a large structure, like a tree, and the pointer to the head of the tree falls to 0. What's going to happen?
Whenever recursion step.
Well, you have a couple of problems. One is that you're going to get a lengthy pause while you free the whole thing up, and you're doing nothing else while you're freeing, right? So you're not running the program, you're just walking down the tree, decrementing counts and adding things onto a free list. So you've got a pause induced from the freeing of a large object. And that pause is limited only by the heap size. In the worst case, the structure fills the heap and you have to wait for the whole heap to be traversed before anything else is going to happen. Another is that we have effectively unbounded recursion here, and you might blow out the stack. The worst case is you have a linked list that's the size of the whole heap. Right? You free the thing, each call decrements and calls free for the next, and you're having one stack frame per object in deallocation, which is obviously not a good place to be. There is some mitigation for that. It's not really a solution, but I would say I should have put mitigation really here, which is that instead of doing all of this all at once, you basically push the free operation onto a thing that you're going to free later, and you go back to processing, because you can take as long as you like freeing things. And you use this list to maintain which things you're going to free, rather than using recursion to do that. And so in the worst case, you're down now to a word of overhead per list item, but it's still, unfortunately, not really a good solution, a good general solution. Okay. the biggest downside of this whole thing is cycles. On that first picture, I had a cycle of two objects with something referenced from the cycle, and I couldn't reclaim all of them because the reference counts didn't fall to 0, and they never will. They'll just stick up, one or more for eternity. And so, in some systems, you can live with that. For example, there are languages in which it's impossible to create cycles. In R, you won't create a cycle. It's all just nested arrays. You can't make cycles, so you don't have to worry about that. But in general, cycles are common in most languages and or easily implemented in a program. They're not common in practice, but they're easily implemented, and you've got to deal with them somehow. So reference counting isn't adequate. You have to have some kind of a backup scheme that's going to deal with it. The easiest thing is to have a separate tracing collector, and we'll look at collection next week. There are schemes which do incremental cycle detection in reference counter systems, but they're basically variants of tracing collection run on small sections of the graph. So you basically run a trial deletion. If I were to delete this pointer, would stuff go away? And if it does, then you're good and you found something. But it's basically tracing, and we'll look at tracing in detail next week. So that is the end for today, with the exception of, well, you set the exercise already. Oh, I have some reading. I don't think I have a slide for it. So there is a paper mentioned in the bibliography, and I'll send out an email on Piazza to read Dave Unger paper on generation scavenging, which is an advanced GC technique. And next week we'll have Dave via Skype to ask him questions about that and anything else related to self or programming languages or virtual machines. So
It's going to be in a different
the auditorium, yeah.
next week.
We'll be in the auditorium and we'll have to go on Skype for an hour. So. Okay.
So, interpreter due today, compiler due next week.
Oh, one last question, quick show of hands, which is we're about a third of the way through now.